Welcome to another session of crystal field theory, which is spectrochemical series of ligands and crystal field stabilization energy. My name is Dr. Jinish. I'm from Department of Chemistry, Ramaya University of Applied Sciences. At the end of this lecture, we will be able to discuss crystal field splitting, crystal field stabilization energy, and spectrochemical series of ligands. We will start with splitting in octahedral field. We studied that the splitting of d orbitals and the splitting in octahedral fielding, which is shown in this figure 1. Splitting of the d orbitals in an octahedral crystal field with the energy changes measured with respect to the barycenter, the energy level shown by the hashed line. We know that the degenerate d orbitals, they are splitted into two sets of orbitals which have different energy. One with lower energy, that is T2g, which consists of three d orbitals, dxy, dxz, and dyz, and Eg orbitals, dz square and dx square minus y square. The energy difference between the T2g and Eg in an octahedral field is represented as delta octahedral. We studied the factors affecting delta octahedral in our previous video lecture, and magnitude of delta octahedral is the strength of the crystal field, and the extremes of the crystal field are termed as strong field and weak field. So here we know that if the octahedral field is weak, then the value of delta octahedral will be lower, and the octahedral field is strong, then the magnitude of the delta octahedral will be high. So we'll be able to write delta octahedral in weak field, which is lesser than that of delta octahedral in strong field. Next topic is splitting in octahedral field. Consider a D1 complex, titanium OH2 6 3 plus. Why we call it as a D1 complex? Because in this, titanium is having an oxidation state which equals to only one electron in its d orbital. So we can write that electron in T2g orbitals. So we can write the ground state as T2g1 Eg0. So only one d electron present in titanium, and that will be in T2g. That's why we have written its ground state as T2g1 Eg0. When a radiation is passed through the above complex, that is TiOH2i 6 3 plus, the complex absorbs a portion of the radiation to transfer one electron from T2g to Eg. And the amount of energy required for the transition depends on the energy gap between T2g and Eg, which is delta octahedral. So the amount of energy required for the transition depends on the energy gap between T2g and Eg, which is delta octahedral. So the energy gap between T2g and Eg is octahedral. So the amount of energy required for an electron to jump from T2g to Eg in this octahedral field, we can name it as delta octahedral. The absorption spectrum of this complex is shown here. We can see the absorption spectrum of the ion exhibits one broad band for which delta max is somewhere around 20,300 centimeter raised to minus 1. So if you convert that delta max into energy change, it will be 243 kilojoule per mole, because we know here the conversion is 1 centimeter raised to minus 1 equal to 11.96 into 10 to the power minus 3 kilojoule per mole. The absorption results from a change in electronic configuration from T2G to T2G1 Eg0. So initially, in ground state, the electron was in T2G. After absorption of radiation in this range, the complex now got sufficient energy for the transfer of electron from T2G to Eg. So the new electronic that arrangement will be T2G0 Eg1. It is very, very important to remember that delta octahedral is an experimental quantity. Now, factors governing the magnitude of delta octahedral and spectrochemical series. First, we will study the factors governing the magnitude of delta octahedral. Nature or identity of the metal atom or ion. It depends on the nature and identity of the metal atom or ion. Second, oxidation state of the metal atom or ion. Third, nature of the ligands, whether they are strong or weak. For octahedral complexes, delta octahedral increases along the following spectrochemical series of ligands. So see the third factor, nature of the ligands, whether the ligands are strong or weak. Based on that, we can actually make an electrochemical series where the ligands are arranged in an increasing order of their strength. So weak field ligands on this side and strong field ligands are here. Here we can see that the same donor ligands with the same donor atoms are close together in the series. Similarly, we can write the trends in values of delta octahedral lead to the conclusion that metal ions can be placed in spectrochemical series which is independent of the ligands. So here, the metal ions are arranged as a spectrochemical series. Spectrochemical series are empirical generalization and simple crystal field theory cannot account for the magnitudes of delta octahedral value. One more important point to discuss before the next topic. Here you see same ligand is having two different positions in the spectrochemical series. Reason here that we studied about ambidendate ligand in the previous video lecture. Here you see NCS minus ion. It may coordinate through either sulfur or nitrogen. So based on that, it has two positions in the series. So if the linkage is happening through sulfur atom, then its position in the spectrochemical series is at the lower position. And if the linkage is happening through nitrogen, then it is having an influence, more influence as strong field, and it is on the right side of the spectrochemical series. Next topic is crystal field stabilization energy, and we will study about high and low spin octahedral complexes also. We now consider the effects of different number of electrons or numbers of electrons occupying the d orbital in an octahedral crystal field. So this is the way that the d orbitals in the central metal ion will be splitted when they are influenced by the ligand. We'll consider a D1 configuration system, which means the central metal atom or ion is having only one electron in its d orbital. So in ground state, we can represent the configuration as T2G1. So in ground state, for a D1 configuration, it will be T2G1, and Eg definitely there will not be any electron. So if you consider with respect to the Barry center, only one electron is present in T2G orbital. So we can write the stabilization energy with respect to Barry center will be 1 into, because only one electron in T2G, towards T2G from Barry center, the energy is minus 0.4 delta octahedral. So we can write 1 into minus 0.4 octahedral for this ion. So the crystal field stabilization energy for D1 configuration is minus 0.4 delta octahedral. For D2 configuration, the ground state configuration is T2G2. So if two electrons are present in the central metal atom or ion, the arrangement will be T2G2 Eg0. So if I arrange the electrons in T2G and Eg, two electrons will be in T2G. And if I draw the Barry center, we know the energy difference between Barry center and for T2G is minus 0.4 delta octahedral. So here two electrons are in T2G. So the total crystal field stabilization energy, we can write it as 2 into minus 0.4 delta octahedral, which is equal to minus 0.8 delta octahedral. Similarly, for a D3 configuration where the central metal atom or ion is having 3 electrons in its d orbitals, then T2G, Eg, 3 electrons are present, 1, 2, 3. So we can write the electronic configuration as T2G3 Eg0. Barry center, energy difference between the Barry center and T2G is minus 0.4 delta octahedral. So we can write the crystal field stabilization energy. Total 3 electrons are there. So 3 into minus 0.4 delta octahedral equal to minus 1.2 delta octahedral. If it is D4 configuration, then little bit difference we can actually see. For a ground state D4 ion, 2 arrangements are possible. The 4 electrons may occupy, all 4 electrons may occupy in T2G sets of orbitals with an electronic configuration of T2G4 Eg0, or may all the electrons are in singly occupied orbital. So the electronic configuration will be T2G3 Eg1. If configuration correspond to a low spin arrangement, here we can see it's a low spin arrangement in 20.3, or the arrangement or the configuration can be in high spin case as in the case of the figure 20.4. Electron pairing energy, which is P, which is the energy required to transform 2 electrons with a parallel spin in different degenerate orbitals into spin paired electrons in the same orbital. So a new term comes which is known as electron pairing energy, which is the energy required to transform 2 electrons in parallel spin in different degenerate orbitals into spin paired electrons in the same orbitals. So here you see here 2 electrons with a parallel spin. For example, 2 electrons with a parallel spin in 2 different degenerate orbitals into spin paired electrons. Here you see it's a spin paired electrons in the same orbital. So the energy required to transform this style of arrangement into this style of arrangement is known as electron pairing energy, which is P. So the loss in the exchange energy which occurs upon pairing the electrons. So to pair the electrons, a loss in the exchange energy occurs, and the Coulombic repulsion between the spin paired electrons. These are the factors which determines the electron pairing energy. Now, Crystal field stabilization energy, we are continuing with that. So for a high spin D4 configuration, as in the case of 20.4, that means T2G 3EG1 configuration, CFSE will be calculated as, because T2G 3 electrons are there, so 3 into minus 0.4 not over. 1 electron is in EG. EG we know that 1 electron is having an energy of delta plus 0.6 delta octahedral. So it will be plus 1 into 0.6 delta octahedral. So the value will be minus 0.6 delta octahedral. Imagine that for if it is a low spin configuration where the electronic configuration is T2G4, then definitely the energy of those 4 electrons, so the crystal field stabilization energy, we can write it as 4 into minus 0.4. All are in T2G. So we can write it as 4 into minus 0.4, that is 1.6 delta octahedral along with pairing energy. Pairing energy we studied. Now, what is the reason behind that pairing energy? So in this case, in T2G in D4 configuration, we have to write that the CFSE will be 4 into minus 0.4, that is minus 1.6 delta octahedral plus P pairing energy.